Okay. Well, happy Friday. Um, so yeah, thanks for wrapping up homework 2. I'll post homework 3 later today, and I should definitely have your homework graded by Friday again. I'll try and have it graded a little bit earlier. So we're still in the middle of methods for asymptotically approximating integrals. We just wrapped up Laplace's methods. The main idea there is to take an integrand involving some exponential with some rapidly decaying function and essentially approximating around the peak of that function. The method that we'll move to next works for Fourier integrals, and it's called the method of stationary phase. The idea is if you have some oscillating function that's oscillating rapidly, then the regions where it oscillates rapidly will tend to cancel each other out, because if you have this first part of your integrand product and it's continuous, then the adjacent values will tend to cancel each other out for the positive and negative lobes of this complex exponential. So if we start with a simpler form of integral, like just I of x equals the integral between a and b of f and t e to the I xt dt as x goes to positive infinity. We'll make a couple of assumptions in order to make a statement about how we might approximate this integral. First of all, that the domain is bounded, the domain of integration, and also that we have as many continuous derivatives as we'd like on that closed interval. Okay, so in general, we're going to call f of t the amplitude of the integrand, and we're going to call xt is going to be called the phase. Okay, and the approach that we take, like a lot of others, first might be to consider integration by parts. So if I integrate up the exponential and I plan to differentiate the f portion, I can rewrite this integral as f of t e to the I xt divided by ix t between a and b minus ix integral between a and b f prime of t e to the ixt dt. We can do this many times and we'll arrive at a sum of these endpoint contributions, k equals 0 up to n of fk of t minus 1 to the k e to the I xt divided by ix to the k plus 1 evaluated between a and b and t plus minus 1 to the n plus 1 divided by ix n plus 1 integral from a to b of f the n+1th derivative of f e to the I x t dt. Okay. And so we'll call this our remainder Rn, and these here are our endpoint contributions. Okay, so far we haven't really done anything that novel as compared to other things that we've seen before. Okay, we're saying, well, I know that x is large. If I integrate by parts, I'm going to keep pulling down these terms of ix. So each successively, each successive term is going to have successively smaller contributions because of this 1 over ix to the n+1 term here. This integral supposedly, as long as it remains bounded, because we have a continuous derivatives here, okay, is just going to have a prefactor that gets smaller and smaller and smaller. Okay, so in general, for this integration by parts approach to work, to be asymptotic, we need to require that the limit as x goes to positive infinity of x to the n+1, Rn of x is equal to 0, okay? And this will be true by the Riemann-Lebesgue lemma, okay? Because we have an integrable function there. So then in general, we can say that to leading order, I of x, or to however many orders we want, I of x can be approximated by this term evaluated at b minus this term evaluated at a. Okay, so if we just want the leading order approximation, we can just take the k0 term there. And because we have an asymptotic series, okay, this should work up to whatever the remainder term is, okay, for any number of terms, okay. So a few things here, right? We're taking a special case of the Fourier integral that I wrote down at the beginning. And in particular, the phase of that is going to be monotonic in t, right? It's just xt, so it just increases in t. Second, the phase change is rapid, okay? And this is key to these Fourier integral approximation approaches in order to get these cancellation effects, right? So for instance, if I look at the real part of e to the t, e to the I x t, for let's say x equals 200, it's going to look something like this. I'm not drawing this so well. But the idea is that your oscillations are so rapid that adjacent lobes of your oscillation are going to end up canceling each other out. Okay? So, you know, this cancels this. That's what we mean by these cancellation effects. Okay. All right. Third remark is that all contributions for this integral approximation are going to come from the endpoints, right? That's what we found in our asymptotic approximation here, right? Because we can build up just these endpoint terms through integration by parts, the remainder is going to be, you know, the integral in between. But our main contributions to all terms in our asymptotic series are going to be from the endpoints. Okay. And so the reason this happens is that those oscillations are not complete. Okay, they don't include a full period. Okay, so because we have a finite domain, if it's not matched to the period of this oscillation, it's going to start and stop at different effective phases. Okay, now if it is set to the same period, then these terms can end up canceling out, but typically this is not the case. So that's the reason why you just get these endpoint contributions, is that the main kind of leading order and you know, several orders up contributions to this approximation are just from the fact that A and B sort of start and stop at different you know, effective phases, you know, offset by whatever multiple of 2 pi. Okay. Whereas the interior points provide you with these cancellation effects. Okay. So that's an integration by parts approach. We're still not really into stationary phase, and we've done this now for kind of the general case of some amplitude times e to the I xt. Okay. Let's now look at kind of a next level up Fourier integral, where we have something beyond just a e to the I xt term there. What if we have a quadratic term there? Okay. Any questions before we move on from this? Yeah. So hopefully that gives you a sense of the mechanics of these Fourier integral approximations. Let's consider the following integral now. So let's say I have e to the I xt squared dt as x goes to positive infinity. Okay. And I want to rearrange this to be a simpler integral, so I'm just going to rescale by square root of x. I get I of x is equal to 1 over square root of x, integral from minus a square root of x, a square root of x, e to the I tau squared, d tau. Okay. Now this is close to a Gaussian. If I make another change of variables, I can write minus s squared is equal to I tau squared. So then tau equals square root of I s. This is equal to e to the I pi over 4 s. Okay. So I of xt is approximately equal to e to the I pi over 4 over the square root of x integral. Now, these limits are quite large, and they're going to be in the tail of some exponential. So I may as well just extend them out to minus infinity and infinity. And then I have a Gaussian integral that I can compute, and I end up with e to the I pi over 4 square root of pi over 4. And that's going to be independent of our endpoints here, right? Because this is just so large that it's gonna push this out to out to the limits here, right? So you may say, well, at this point, it was a complex exponential, right? But once we made the conversion um, a to just a regular real argument function, okay, we can take this integral out to the minus infinity and infinity limits because the exponential decay is going to be so great that you're going to have extremely small values out at the limits of this. Okay. So there's two reasons to derive this integral. One is that it's kind of a starting point for some of the things we'll do with other Fourier integrals. But actually, this integral comes up a lot when we're performing Fourier integrals, okay? This e to the I x t squared, as you would imagine, if we have something like psi of t, and we do some Taylor expansion, okay? One of the first terms that we're going to come to is a quadratic term. So you're going to run into this integral a lot, okay? So it's good to know, the formula for working it out, okay? I have a little typo here. Yeah, for some reason I wrote 4 there. That shouldn't be a 4. That should be an X. Okay. All right. So let's talk about then the general case, okay? So now we're sort of armed with a way of handling a more general case, which is back to our regular Fourier integral, e to the I x psi of t dt, okay, where psi that just means it has real outputs, okay? Now let's talk about a few cases that could arise here. Let's say that f of a is not equal to 0, or f of b is not equal to 0, and psi prime of t is not equal to 0 on our domain here, okay? F and psi are both C1, okay? Then I of x is going to be big O of 1 over x as x goes to positive infinity, okay? Now this was not the case with our previous integral, right? Which is why we didn't get something that was big O 1 over x. We got something that was big O 1 over square root of x, right? So now the other case to consider would be if phi prime of x is equal to 0 somewhere in the middle. So let's call that our point C there, okay? And now we're dealing with another case that can be handled just by integration by parts, right? Our earlier case that we worked through in general, right? It was sort of this case. It was fine. You can use integration by parts, okay? But now let's say we have some critical points of psi, okay? So for example, I of x was this integral that we dealt with before, okay? So at c equals 0, you have a critical point. Well, in this case, what you expect in general is that I of x is going to be big O of 1 over square root of x as x goes to plus infinity, okay? And maybe you can hand wave yourself into seeing why this would be, okay? Because you have something quadratic, right? And so the amplitude of that quadratic or sort of the units of that quadratic are going to kind of be square root of x. So sort of the scaling of that quadratic, okay, as it moves away from this critical point is going to be something like square root of x, right? So maybe that's where this 1 over square root of x comes from in the order. Okay. So more generally, to leading order, right? We are going to have this for a variety of functions that we can essentially, approximate by their quadratic terms, right? Of course, there's going to be some caveats to this, like if the quadratic term is 0, then you may have larger scalings or something like that. But this holds generically. Okay. All right. So there's then 2 approaches to this. Okay. And case 1 is the one that we talked about already, right? Is integration by parts. If phi prime is not equal to 0, and let's say, for instance, phi prime is greater than 0, we can change variables. Tau equals psi of t, d tau equals psi prime dt, t equals some function out t of tau. It's going to be single valued because we don't have any critical points of psi, right? So we don't have to worry about bad things happening if we invert that function. I of x then is going to be equal to psi of a, psi of b, e to the I x tau, f of t of tau divided by psi prime t of tau. That just comes out of our change of variables. Integral now from psi b to psi of a, g of tau, e to the I x tau. Okay, so we can absorb everything into that g. Now using integration by parts and our Riemann-Lebesgue lemma to just make a statement about how that remainder is going to remain bounded and going to sort of scale properly to give us an asymptotic expansion. I of x is going to be approximated by e to the ix psi of b divided by ix g of psi of b minus e to the ix psi of a divided by ix g of psi of a. That's just going to be your boundary terms. And we can write these out as then minus I over x, factoring out e to the ix psi of b, f of b divided by psi prime of b minus e to the ix psi of a, f of a divided by psi prime of a as x goes to positive infinity. Okay, so this is effectively what we did before. We're just keeping the leading order term. Okay, but now we've extended it to the case where you can have any function psi of t as long as it satisfies this assumption that psi prime is not equal to 0, and in this case psi prime is greater than 0, right? But you can always change variables so that you flip the sign of this, and everything is going to obey this case. So you can make this assumption sort of without loss of generality. It'll work in a monotone decreasing case as well. Okay, so that's not that new as far as what we've discussed so far in this lecture. Now let's talk about case 2, which is going to be our method of stationary phase. Okay. Case 2, on the other hand, is if we consider one point of what's called stationary phase, and we'll say at t equals a without loss of generality. Okay. If it's t equals b, it's going to be similar. It's just going to be at the right end instead. If it's on the interior, you're just going to cut out a region to the left and to the right, sort of right around c, as we've done for Laplace's method, right? So in this case, right, we just have some region right around here where we're going to approximate by whatever the integral is here, okay? And then this part is going to be much smaller over here, okay? So this will be our sort of I1, and then this I2 over here will presumably be much less than I2. Okay, so our stationary phase region is going to be our main contribution to our integral. Okay. All right. And the reason that this part is going to be a lot smaller, it's going to be order 1 over x as opposed to the stationary phase region, which is going to be order 1 over square root of x, is that if there's no stationary phases in this part here, you can treat this as you would in case 1. You could do integration by parts. So if you just want the leading order terms, you can just look in this little region around the stationary phase. Okay. All right. So in that region, phi prime is equal to 0. We'll say that phi prime prime is greater than 0 for now. I of x then is going to be split up into integral from a to a plus epsilon f of t e to the I x psi of t dt plus integral a to the epsilon up to b f of t e to the I x psi of t dt. As we said, this is going to be order 1 over x as reported in case 1, okay, for any epsilon greater than 0. So we could shrink down epsilon as much as we want. And now this thing, we'll call this I1 of x. Okay. So now let's compute I1 of x. I1 of x is going to be the integral from a to a plus epsilon f of t e to the I x psi of t dt. Okay. And what do you think we're going to do now?
Expand psi.
Yep. And
extend the endpoints.
Yeah. And expand f as well.
Yeah.
Right?
Okay.
So really not a lot different than Laplace. It's just that we have a complex exponential now instead of a regular exponential. Okay. So we're going to expand f of t is going to be to leading order just f of a, right? Because around here, the main contribution is going to be right at t equals a. So the amplitude that's going to matter is the one at t equals a. And so as Jake said, psi of t is going to be the leading order psi of a plus, we know that psi prime of a is 0. So we can move all the way up to psi prime prime over 2 t minus a squared. Okay. Okay. Moreover, you can change variables after this, but I'm just going to write out now this leading order approximation. So we have f of a e to the ix psi of a integral from a to a plus epsilon e to the I over 2 psi prime prime a t minus a squared x dt. Okay. Now, if you look at that integral, it's not so much different than the one we did a couple pages ago, right? It's just it's a complex exponential with a quadratic term in it. Okay. There's a few ways we can handle that. We can use the integration technique that we used before. You can also use Cauchy's theorem and contour integration in order to integrate it. Okay. But let's clean it up a bit just to show that we get, the nice sort of well-behaved integral that we worked out before. So I'm going to change variables. Tau equals phi prime prime of a x over 2 t minus a. Okay. So just to get most of the gunk out of the exponential argument. So I get I1 of x. Well, I guess I already said that this term is asymptotically smaller. So we can just say this is I of x now is approximated by that. E to the ix psi of a integral from 0 up to epsilon times x psi prime prime of a over 2 e to the I tau squared e tau. Okay. Now we have an epsilon, okay, but we have an x. So as long as we take epsilon not too vanishingly small, right? However small epsilon is, it will be dwarfed by the size of square root of x, okay? And as long as this is non-zero here. So per usual, we can take the integral all the way out to infinity. You can extend the range of integration, okay? I1 of x, let's just keep that as I of x, is then to leading order 2 over x phi prime prime of a square root f of a e to the I x psi of a integral from 0 up to infinity e to the I tau squared e tau. Yeah, I think that I might have forgotten this leading order term here. Yeah, I forgot to include this over here. 2 over x phi prime prime of a. Sorry about that. Okay. All right. So how do we compute this integral? On the next slide, I'll show how to do contour integration in order to compute this. Okay. But essentially, we get a square root of pi over 2 coming out of it. Times, and then we still have our same f of a. And we also get this additional I pi over 4, okay? So if you remember back before, we had this integral between minus infinity and infinity. We just cut that in half in order to get this integral here, okay? So if I flash back to this integral here, right? This integral from, minus infinity to infinity. Without the x, I would just get a square root of pi here, e to the I, pi over 4, okay? But then it's just half of this, so I get the integral from 0 to infinity, okay? All right. Have people done this in complex analysis before? This kind of integral before? Or if so, remember doing it?
It's been a while.
Do you want me to go through that calculation? I have it. I can go through it if you want.
Yes.
Okay, I will go through it. Okay. All right. Yeah, I won't teach a whole lot of complex analysis in the course, but maybe this is a good chance just to do a quick complex analysis example using Cauchy's theorem. Okay. Any questions about this before we move on? Sorry, this is sort of smushed. I can rewrite this on the next slide. Okay. Yeah, so I'll just rewrite that formula just because it's a little bit of a mess there. But so you get I of x to leading order is the square root of pi over 2x phi prime prime of a times f of a e to the ix psi of a plus I pi over 4. Okay. All right. Now, basically, to get this integral, we're going to deform our integration contour, okay? And in general, we can use Cauchy's theorem, okay? So there's no singularities here, okay? So if I define the following domain or contour to integrate around, okay, I can include a portion of the contour that's going to represent the integral that I'm interested in. I'll call that little gamma 1. I have little gamma 2, which is going to be an arc that goes up to pi over 4. And then I have another section of the contour, which travels back to the origin in the complex plane. Okay. So this point here, I'll call r e to the I pi over 4. Okay. This part here is just going to be r. And then back here, we're at 0, okay, for both the real and imaginary part. Okay, so this whole thing I'm going to call gamma, and I'm going to be interested in computing e to the I z squared dz. Okay, now by Cauchy's theorem, there's no singularities in here. This whole contour integral then should be 0. Okay, so I can extract this integral by equating it to the remaining portions of the contour integral. And that will give me my desired result, okay? So let's split this up, right? So we can write this as the integral over gamma 1 plus the integral over gamma 2 plus the integral over gamma 3 of e to the I z squared dz, okay? If I write that out in detail, I have the integral from 0 to r of e to the I z squared dz. That's my integral that I'm interested in as I take r to infinity, okay? My second integral is going to be the integral from 0 to pi over 4 of e to the I. Now it's r e to the I theta, quantity squared, I r e to the I theta. Just made the change of variables to theta, e theta there. And in addition, now I have an integral from 0 to 1, e to the I r e to the I pi over 4 times 1 minus t. So it's tracing back to the origin from out here at this point. Okay, that whole thing squared. And I also have, what do I have? Yeah, I have times, so this is kind of smushed, minus r e to the I pi over 4 dt here. Okay. All right, because I had to change variables between z and this t parameterized version of this contour. Okay. So this is just giving me how I trace from here back to here. This term comes from that change of variables in z. Okay. And so now I just have 3 integrals. I only need to compute 2 of them, and then that will give me the value of the remaining ones here. So this whole thing is equal to 0. Okay, let's deal with the arc first. The arc is going to be given by its absolute value from that integral. I'm going to be able to show that it should vanish as r goes to infinity. Okay. So I can bound this from above by the integral from 0 to pi over 4 of r e to the minus r squared sine of theta d theta. And this is bounded from above by the integral from 0 up to pi over 4, just bounding that sine, e to the minus r squared 2 over pi times theta, e theta, okay? And then lastly, if I integrate this up, I get minus pi over r e to the minus r squared over 2 plus pi over r. Everything's going to decay to 0 as r goes to positive infinity. Okay, so just by a sequence of boundings, now I've ruled out this part of the integral. So essentially, this integral now is just going to equal whatever this is. And this is a doable integral here, even though it looks a bit complicated. Okay, so the idea now is the integral from 0 to r of e to the I z squared dz is equal to r e to the I pi over 4. Now you see that term starting to show up. The integral from 0 to 1, you would imagine this is going to generate some factor of 1 over r to cancel out that r out front. R e to the I pi over 4, 1 minus t whole thing quantity squared dt. And that's going to hold as r goes to positive infinity. Okay. So I'm going to make a change of variables. Okay. U equals RT in our second integral. And our second integral now is going to look like R e to the I pi over 4, integral from r up to 0, e to the minus u squared minus 1 over r du. These r's are now going to cancel. Okay. And this is an integral I can do. It's just going to be a Gaussian integral. And so I get the square root of pi over 2 e to the I pi over 4. Okay. As r goes to positive infinity. Okay. All right. So that's our result. So we now have two ways of getting that integral that's going to show up a lot when we use method of stationary phase, and we want to get that leading order term. Okay. All right. We got about 5 minutes left. Let me talk about the more general case, and then I think that'll lead us up to an application that will springboard you for one of the homework problems that'll be on the next homework. Okay. So the more general case is, let's say I of x equals integral from a to b, f of t e to the I x psi of t dt. Okay. Let's say that phi prime evaluated at c is equal to 0. And then phi prime of t is not equal to 0 elsewhere. Okay. And also f of c is not equal to 0. Okay. In general, if phi prime of c equals phi prime prime of c equals phi prime 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 of c, and so on, all the way up to phi p minus 1 of c. If all those equal 0, then you're going to do like we did in Laplace's method, and you'll just consider the expansion psi of t equals psi of c plus psi p of c divided by p factorial t minus c, excuse me, to the p. Okay. All right. So assuming that the peak derivative of psi is at c is not equal to 0. Okay. So in that case, okay, our leading order term is going to be f of c e to the I x psi of c plus I mu pi over 2p, okay, times p factorial divided by x psi of pc to the 1 over p root there, gamma function of 1 over p divided by p as x goes to positive infinity. Okay, where what's mu? Mu is just going to be the sign, S-I-G-N, of psi of p. Okay. All right. So you see here maybe how this is a generalization of what we wrote down before, right? Instead of just having pi over 4, right, we have whatever your leading order contribution term is, okay? That's going to be the fraction of I pi that you're going to use in that case. And you see this peaked root is going to come from having terms of order, t minus c to the p in your Taylor expansion in your exponential, okay? But in general, your typical case, I'm almost done, don't worry. Your typical case is going to be, of course, p equals 2. And in that case, you have this nice formula, which I can write out, which is f of c e to the I x psi of c plus I mu pi over 4 square root of 2 pi over x psi prime prime of c. Okay, so we see the 1 over square root of x scaling showing up there. We see that this factor of psi prime prime of c is also going to determine the scaling or the amplitude of our leading order term. Mu again is going to be the SIGN of psi prime prime. Okay, and in general, if psi prime of Cj is equal to 0 for a lot of points, we talked about this sum, I think in the last class or before, you're just going to sum over each contribution, okay? And so the principle in general here is find where psi is stationary, where you have stationary phase, okay? Where you have a turning point, basically, in your function psi, okay? Expand about that point to second order or however high of order you have to go to. Use these ways of computing that. Integral over, e to the I tau squared, although you can just go ahead and use that formula now that we've derived it twice. And if you have multiple of these turning points, then you just sum over these contributions in this case. So in general, it should handle most situations that you would run up against. If you want to go to higher order, as you'd imagine, you have to expand to higher order in your amplitude as well as your phase. But typically, these leading order approximations should be fairly accurate as long as x is large. Okay, that's all I have for today. Any questions or comments?
Oh, on the last page, what word did you write, like middle of the page on the far right? It was next to psi prime of C, psi prime of P.
Oh, elsewhere, sorry. Yeah.
Okay.
Elsewhere, yeah. So,
Okay.
and it's fine if you have critical points at other places. If you do, then you just do an expansion around each of them, and then you add all those up. And if some are of smaller order than others, then you get rid of them, right?
Sounds good.
As
Thanks.
you can see here, right, the ones that are like quartics or cubics or something like that are going to be leading order, right? So, whichever one is associated with the highest derivative here would be the one that you would retain. But typically you're going to have, generically you're going to have second order derivatives determining your expansion. Okay, so that's method of stationary phase. On Monday, we'll talk about an example as applied to dispersive wave equations and sort of linear PDEs in general, and also Schrodinger's equation. So a couple of PDE examples. We'll finally get into some PDEs. And then we'll introduce a method of steepest descent. And then we'll be done with integrals and be moving on to differential equations for pretty much most of the rest of the class. Okay. All right. Well, if there's nothing else, yeah, I'll post homework 3. That deadline is going to be in 3 Wednesdays, so March 3rd, and then we're going to stick to Wednesday due dates after that for homework. So I'll try and give you regular reminders of that. It's only 5 problems, so yeah, hopefully that's plenty manageable for you all. So otherwise, yeah, have a good weekend, and I'll see you on Monday. And don't forget, there's a wellness day on Wednesday, so no class on Wednesday. All right.
Thank you.
You.
Y'all. Yep. Have a good day.
Thanks, Zach.
Bye.